Okay. Okay, give me a moment, please. Welcome to a new session of this. Empezaste. Okay. Welcome to a new session of this Latin American seminar on set theory called Seminario Colombo-Mexicano de Teoría Conjuntos. Today we have a special speaker. He's a Polish mathematician. He's Professor Sławomir Solecki. He works at Cornell University in USA, and his field of expertise is descriptive set theory and its application. Then, thank you so much, Professor Solecki, for accepting our invitation to give a talk in this Latin American seminar. We are so happy with your participation, and we can start with your talk. Thank you, Professor Solecki.
Okay, thank you, Julian. Thanks for the invitation. Very happy to be here. Okay, so I'll talk about descriptive set theory and generic measure preserving transformations. Wait a second. Okay. So okay, so the talk it's mostly about it will be about interactions between descriptive set theory and ergodic theory. So I will start with a short review of what of basic notion of descriptive set theory. I apologize if everybody is familiar with them, but it will be a short introduction, so not much harm will be done. So the important notion here is that of a Polish space. So this is a metric separable complete metric space. And a very important role will be played by a certain notion of smallness called meagerness. So just for completeness, a set is called nowhere dense. These are the building block of meager sets. So nowhere dense, if its closure does not contain any non-empty open set. So it's a set that doesn't, essentially in every part of the space, in every open set, there is a hole avoiding the set. So these are nowhere dense sets. Meager sets are countable unions of nowhere dense sets. Important thing is that obvious that meager sets are closed under countable unions, and their complement, the complement of a meager set is always dense. So this is a very good notion, topological notion of smallness. So if a set of points is meager, this means it's a small set. And comeager, I will use the word comeager to indicate that it's a set whose complement is meager. And finally, there is this linguistic convention that I want to introduce that's used in the area. And the convention is that I will say, given a space X, that a generic element of X has property P. So I will be given X and I will be given a P, property of points of X. A generic G has this property precisely when the set of G's having the property is comeager in X, comeager in X. This should be in X. And so there are various other notions of being comeager, but we have this kind of simple one in mind, and I will not change it throughout the talk. But this is an important notion. So it's a notion of measurability. There is a notion of measurability associated with meagerness. So I will talk a little bit about this introductory notion, and this is the notion of having bare property. So a set has a bare property precisely when it differs. So a set A here has a bare property if it differs from an open set by a meager set. So I can throw away from a meager set and add to it possibly a meager set, and now I will have an open set. So a set as nice as possible. So important, why is that? I mean, why is this notion of an interest, this notion of visibility, measurability? The one thing is that and this will be crucial, it behaves well. It's a good notion for groups that are not locally compact. So if a group is not locally compact, Polish groups, so with the Polish group topology, then there's no hard measure on it. But there is notion of measure theoretic notion of measurability, but we will have this topological notion of smallness and this topological notion of measurability. I'll come back to it later. But structurally speaking, This is a very nice notion. So it does fulfill a Fubini type theorem in product spaces. So so this is the usual thing that if I am in a product space, I have a measurable set, so bare property. If most sections, vertical sections are meager, then most horizontal sections are also meager. This is an important point that this theorem of this type will enter in the proofs of the main theorem that I will in a crucial way. So what are these Polish groups? I already alluded to Polish groups. So groups that carry these are topological groups whose group topology is a Polish topology, so metric separable and complete. And as I already mentioned, there is no Haar measure on such groups unless those groups are locally compact. So if I have a locally compact group, there is a standard notion of measurability there, and standard notion, a unique notion of measure theoretic translation invariant smallness, namely having Haar measure 0. But if the groups, and these are all the groups I will be talking about today, are not locally compact, such measures are not available. On the other hand, meagerness and having the bare property are still there to help us. So examples of the groups that I will be talking about. So as I mentioned here, I will be talking about non-locally compact groups. So no Haar measure. There's many examples. Here's a list, but there will be 3 particular examples that will play a special role. And so we'll take a look at more closely at these examples. But here is just a short list. For example, separable Banach spaces with addition of vectors, homeomorphism groups of compact metrizable spaces, or isometric groups of Polish metric spaces. So many examples of that sort. And now the most important groups. So I mentioned I will talk about Polish groups. The basic example for me will be the group of measure preserving transformations. So what I have here is I will denote this group by odd. This is the group. What am I looking at? I will look at the interval 0, 1 with Lebesgue measure. And I will look at all transformations or bijections of the interval 0, 1 that preserve the Lebesgue measure. So these are bijections of 0, 1 preserving Lebesgue measure. I don't actually take transformations, but I will take their classes, measure classes. So I will identify 2 such transformations if they coincide on a set of full measure. So odd is the group of all measure classes of measure preserving transformations. Now, here, I should maybe say so this is a group with composition as a measure, as the group operation. And there is a unique, really Polish group topology on odd. So this group topology is what they call the weak topology. And it's a classical topology, very easy to define. Let me just say here that a sequence Tn converges to T if the following thing happens. For each, if I pick a Borel subset of 0, 1, I do the following measurement. I take the image of A by T. I take the image of A by an element of the sequence. I take the symmetric difference here. This is the symmetric difference of the 2. And then I make the measurement on that symmetric difference, namely I take lambda. So this is the measure of the symmetric difference. And no matter what set I pick, this sequence here has to converge to 0. So for each A separately, this sequence converges to 0. It's important to point out that here on this side, in this measurement, I don't really care about A, but only about its measure class. Otherwise, I would be in trouble because T and Tn are not really transformations. They are really measure classes. So, but this is just a subtlety here that won't be important. But in any case, so this is the main group. And this is an interesting example of a Polish group, but it's much more than that. So this group is really the domain or the universe of ergodic theory. So one can, in essence, one can say that the ergodic theory is a theory of elements of that group, either constructing them or looking more globally at properties of the group or parts of that group. I should also mention here that this may be, so this is actually, it's an important, a group that has its own importance. I should mention here also this, that this might look very specific, taking the interval 0, 1, but this is only to fix attention. In fact, I could have put here any Polish space and any Borel probability, Borel measure on that Polish space, and then run the same definition for that general Borel probability space on a general Polish space, and I would get an isomorphic group, this isomorphic as a topological group to the group OT. So it doesn't matter really what on what set, on what Polish space my measure resides. It doesn't matter what kind of a measure it is. I always get the same canonical group. Okay, so as I mentioned, some important results in ergodic theory can be viewed as results about this group. In particular, there is a specific equivalence relation on OT that is of special interest. So this is the equivalence relation essentially of isomorphism. I have two measure-preserving transformations, so elements of OT, T1 and T2, and I would consider them as isomorphic if they differ only by a change of coordinates, by a change in the arrangement of the points on which they are defined, which amounts to saying that I consider them, I identify them if they are conjugate to each other by an element of S. So this is an important equivalence relation, and quite a lot of results in ergodic theory were proved in order to understand this equivalence relation, classify it on some subsets of OT, or prove that it is difficult to classify. And in fact, so this will come back to that equivalence relation. There's also another theme in ergodic theory. It's namely the theme of so one theme is studying this equivalence relation. Another theme is looking at generic elements of OT. So I'm treating here OT as a Polish space, and I'm interested in properties of elements of OT that are generic. So properties with such that the number of elements, the elements of OT fulfilling the property forms a Komiger set. So there's a long history, and there is apologies. I gave a similar talk at the seminar here at Toronto. I made the same joke, but I cannot help myself. So there is it was an interesting sequence of papers in the 40s. So this is a long history. It started in the 40s with a paper of Halmos. So this is the Western point of view. Halmos wrote a paper titled, in general, a measure-preserving transformation is mixing. By general, he meant a generic. So a generic measure transformation is mixing. And 4 years later, Soviet Union answered by proving, in the person of Rocklin, a paper was published in the East saying a general measure-preserving transformation is not mixing. So the direct contradiction to the Halmos paper. Fortunately, it wasn't really a mathematical contradiction. Rocklin was talking about strongly mixing transformation. Halmos was talking about weakly mixing transformation. So everything was resolved peacefully. The main point that I'm making is that this study of generic elements has a long history. It's really from the 40s, it's almost the beginning of ergodic theory. Okay, so there will be two additional groups that are, so OT is the main group I will be studying. There are two additional groups, so one of measurable functions and another group of unitary transformations of a Hilbert space. So let's start with, I want to introduce these groups. They play, so L0, this is the group of measurable functions, will play a crucial role in the statements. The unitary group enters actually through the proofs. So the role of the unitary group will be auxiliary. So L0, so what is L0 here? So this is I look at measurable functions going from the interval 0, 1, Lebesgue measurable, to the unit circle. And I consider those functions again up to measure equivalence. So I'm not really thinking about the group of functions, but the group of equivalence, measure equivalence classes of these functions. So this is a Polish group with a group operation is pointwise multiplication. The topology is the topology of convergence in measure. So this is the simplest topology on measurable functions. In this case, because the values of the functions are bounded, they are in the unit circle, it doesn't really matter so much, it doesn't really matter at all which LP topology we pick on it. We can take any LP topology with P less than infinity. They coincide on that group L0. But this topology of convergence in measure is probably the nicest one. Doesn't involve the integral, for example, at all. So let me just, if you don't know what the topology is, doesn't matter so much. It's important. It's a natural topology on the space of functions with the measurable functions with values in the circle. So the unitary group, that's the second group. It's a very important group in mathematics in general. So I would denote it by script U. So what we take here, we take an infinite dimensional, so large but separable complex Hilbert space, and I look at all unitary transformations. So it's the same definition as in linear analysis. So these are, let's say, transformations that preserve angles, and I make, so again, I take it with composition and I make it into a Polish group using the so-called strong operator topology here. It's again, there is a unique Polish group topology on that group. So there is one choice here that I can make, and this is the choice that I do make. So strong operator topology that just say it's a natural topology on that group. So I look at all these angle preserving transformations of this big space, but controllable, and I put a nice topology on it that makes it into a Polish group. Okay, so now, are there any questions about these groups that I introduced? Okay, so if not, let's move.
Maybe a little bit out of curiosity, but yeah. What would be, for example, what would be the complete metric?
Here in the unitary group?
Or in those, how would the metric look?
Okay, there will be, it's always in L0, you just write it out, but it's probably easiest to look here because I already have the formula. So what you would do here, you would to measure the distance between S and T, you would look at S of a symmetric difference T of A. And okay, you cannot take, you would want to take a sum. You would not want to take the sum over all Borel sets. So what you do is you fix an algebra, countable algebra of Borel sets, and you enumerate it into a sequence AN, and you make these measurements on the elements of the algebra. Then you put a weight here so that the series converges, and then you put ST, you consider this sum. This is a metric on that group that gives you the right topology, but this metric is not going to be complete. What you have to do additionally, you have to add to it the same sum, except that you take the inverses also. And now with these two components, this is a complete metric on the group odd that gives you the right topology, right? So this is the kind of tricks. The important thing here is to take the sequence AN countable. It has to be countable, but it has to be rich enough. So it generates, so it's an algebra of sets So finite intersections, finite unions, closed under finite intersections, finite unions, and complements that will generate the sigma algebra of Borel sets, generate as a sigma algebra. So this is here in L0, you would put, there is a standard metric. Let me note, this is easy to do. And here in the unitary group, you do the same trick as for as in odd, except that you have to take, instead of an algebra of sets, you take a dense countable subsets of vectors, and you form certain sums, u vn vn, and then you subtract, you take the norm, and then you sum with appropriate weights. You have to take minimum here with 1/2 to n, minimum of this and 1, and then you sum it up. And then you do the same sort of thing with u minus 1 and v minus 1, and you have another component. That's what they look like. Is that all right?
Yeah, and if we don't do the trick of adding the inverses, it is not complete, but it is invariant by the group action, right?
Yeah, that's correct. This is correct. So if we don't do the trick with inverses, it is not complete, but it will be what? It will be, I mean, let's see, it will be a right invariant, right? It will be, I think, right invariant. If we just have this situation, or left invariant. Actually, this will be left invariant. So it will be an invariant. It will give the same topology as after adding the inverses, but it will not be complete. If we add the inverses, we get completeness, well, we lose invariance. So that's what it is. That's correct.
In this definition, the symmetric difference is a Meager set, really?
No. Here.
Yes.
Are you talking about this?
No, this symmetric difference. Tn of A, different symmetric difference Ta.
Are you talking about this slide or a different page?
Yeah, is this a slide?
No, yes, okay. So these are not meager. No, they are not meager. This has nothing to do with meagerness. So this symmetric difference here is computed in the measure space. So this is A is just a measurable set, and I take T of A, S of A, it takes a symmetric difference, and I make a measure theoretic measurement on it. I'm not concerned about meager, not meager. So what I will be meager, not meager is something global on that group. Not on the level of the space on which the transformations are acting, but on the level of all transformations. This is where meagerness, not meagerness, comes in.
Okay, thank you.
Yep. Okay. All right. Any other questions? Okay. So let's so measurable functions and then u. Okay. So now let me do so this is the subject matter of the talk. So, okay, good question about meagerness, because now this is where it will be key. So, so the subject matter of the talk is this. For a Polish group G, I can always consider, so these are the objects that I would be considering. I will consider the following. So this is a general Polish group, but I will really only be applying it when G is odd. So I look at the group generated by G, so positive and negative powers. So this is just an abelian group. Is either Z or it's a cyclic group, finite or infinite. And then inside of this G, I take the closure. So now this is again an abelian group, as being the closure of an abelian group, being the closure of this group here. But of course, the closure in general will add many new elements. So this group in general will be an uncountable group. So still I will be denoting this group, the closed group generated by G, as, okay, group generated by G with C here for closure. So this is the main object. If I have a Polish group, I will look at closed group generated by elements of G. And then the main point will be, I will look at the group of odd, and I will be interested in generic elements of odd. So I will be looking at sets, Homiger sets of elements of odd. I'll be taking an element of such a Homiger set. I'll be generating a closed group using that element. And I will be asking what kind of properties these closed groups have. So again, so I'll be looking at, for every element T in odd, one can look at this closed group. So this is a closed subgroup. This is a closed subgroup of odd, closed. And one can ask about properties of this closed subgroup of odd. And I will be interested in properties that these groups have for a generic T. So properties that when I look at what T's have, for what T's these groups have that property, the answer will be almost all of them have that property. So this is the subject matter of the talk. I'll have a concrete question, not just that this is just an intro, but I'll have a concrete question in mind. Is that clear what I mean? So again, genericity will be, or meager, comeager, this is on the level of the group. And now I'm looking at, okay, although I will look at, these are the groups whose properties I will be looking into, and I will be only interested in properties of those groups that hold for comeagerly many T's coming from odd. So that's the point. And somehow, so what's the, so I will ask a concrete question. I want to motivate this question from kind of general point of view, and then give several results that had been proved in the literature that indicate that that what the question is asking about is reasonable. So first, a general kind of motivation for the question. So there is this, I indicated already that this is an important equivalence relation on odd. This is something ergodic. This is something, I mean, if you could classify this relation, classify this equivalence relation, that would be absolutely amazing. But that's not possible. So this is an equivalence relation on odd, and this relation is known to have a complicated behavior. So even for a generic element, so even if you throw away a meager subset of odd, so you leave only a comeager set, so you have, this is your odd, you throw away a meager set, on a comeager set, no matter what meager set you throw away, on what is left, this equivalence relation will have a complicated behavior. And let me not go into it. There is an old result of Rochlin about it, and there is a very powerful recent result of Forman-Weiss. From the descriptive set theoretic point of view, this is a very complicated equivalence relation, even on comeager sets. All right, so the situation looks bad, and that for that reason, so ergodic theorists would, well, that reason, maybe other reasons too, but this is one of the reasons. The ergodic theorists looked at the following much more generous equivalence relation, namely this one here. So this equivalence relation, in this equivalence relation, I identify T1 and T2. If these two groups, I generate these two closed groups, and I require that they are isomorphic as topological groups. So isomorphic as topological groups. And then I say T1 and T2 are equivalent with respect to this equivalence relation here. So that's easy to see. It's an equivalence relation. It's more generous than this one here, because if T1 equals S T2 S minus 1, then it's immediate that the closed group generated by T is actually also equal to the conjugate closed group generated of the closed group generated by T2. And this conjugation gives actually an isomorphism between these two groups. So here I'm asking not about, so this implies that there is a very concrete isomorphism. I'm asking, I'm even much more generous. I'm saying I identify these two groups, two elements, if these two groups are isomorphic, maybe by an abstract isomorphism, of course, continuous, as topological groups, right? So if they are, this means the behavior of T1 in T2 roughly is the same, but very roughly. So one looks at this much more generous equivalence relation, and one hopes, the hope is here, that this equivalence relation has a much more uniform behavior than this one. Yes, so possibly even one hopes that there is a generic equivalence class, meaning that in odd, we split it up into equivalence classes of that equivalence relation, and there is one equivalence class that contains almost all elements of the group. So it's comeager, one equivalence class that is comeager. So what would it mean? It would mean that there is a comeager set here in odd, such that no matter what two elements I pick in it, the groups, the closed groups generated by them are isomorphic with each other. So this means that for a generic element of my group odd, I get the same group if I generate the closed group by that element. So I'm getting a single group on a generic set by with this generation. So the question was, is that possible? But of course, if you want to ask a question of the sort, you have to have a good guess. So if you say there is for a generic T, that you get a single group, you have to have a guess what this group will be. And Glasner and Weiss asked the following question: is it the case that for a generic T, this group generated by T is isomorphic to the group L0? So they had a guess. Is it the case that in odd, if I take for most points, the group generated by T is actually this group L0 that I introduced? So that's the question I want to look at. So are there any questions about what I've introduced so far? Any questions about the question or the problem?
Sławek.
Yes.
But for a Bernoulli shift or something like this, or an irrational rotation, is it known?
No, yeah, for these are much simpler. So
okay.
For this would be yes. So this would be known. I don't remember now what it is, but they will come out simpler.
Okay. Okay. Thanks.
So this actually okay. So that's a good point. So it makes sense here to ask for a generic T, and the reason is, if you, for an arbitrary T, you will have very different, so people did look at this, you get very different behaviors. Each group may be even countable, they may be even finite. Finite, they can be finite, they can be countable, so all points isolated. So they can be, the behavior may be very, very diverse if we don't look at the generic T. So that's a good point. But so this is important that we look at generic T. And any other questions? Okay. So now the question is why this guess? Why L0? So I want to now say, why would people think it might be L0? So motivation for the question is, so first of all, this group qualifies. So Glasner and Weiss proved that there is a T, there is some T for which we do get L0. So at least it's not ruled out. Notice this group here is abelian, and this group is abelian. So there's some match here. This group, there is a single element of this group, as proved by Glasner, that will generate this group as a topological group. That's clearly the case also here. So these groups are very roughly speaking similar, and actually this L0 is represented among closed group generated by some T's. Then there was some analogy, a theorem due to Melleret and Sankov showed that if you don't go to odd, but to a closely related group U, then for so this U, this is the Hilbert is the unitary group. then for that, if you look at generic unitary transformation, you indeed get a group isomorphic to L0. So for unitary transformations, you do get L0. So if you think these two groups are somehow analogous or related to each other, you may hope that something like this also happened to odd. It's important to point out here that U is included in odd as a closed subgroup, but also odd is included in U as a closed subgroup. So they are related to each other. So they are, and there is also here in the analogy, I don't have this result, but there is another result about a certain subgroup, Gaussian transformation of odd, and one also gets L0 there in the generic situation. So there's some analogy. Then there was a lot of results in the Russian school in ergodic theory on the structure of these sort of groups. The first one was proved by Ageyev, who showed that for a generic T, these are rather large. So each finite abelian subgroups is included in that group. So this, why is it indicative that this might be L0? Well, the reason is if L0 very easily has this property. One can very easily show that L0 has this property. So if for a generic T, this is L0, you get this for free immediately. But okay, so we have this indication. So I also here, I made a contribution some time ago that for a generic T, well, let me maybe not go into why that relates to L0, but for a maybe I will say a word about it. For a generic T, there is a Polish linear space. So a linear space with a Polish topology. It's not a Banach space, but it has a Polish topology that respects the linear operation. And there is a continuous surjective homomorphism from that linear Polish space onto that group for a generic T. And notice it's quite easy. Let me just write it. If I look at L0 with values in R, there is a natural F goes to EIF, the natural exponential map, which is a homomorphism from that group to that L0 group. And this is a Polish linear space. So again, if this were L0, that would be for free. You would get it immediately because of that, because of this general, so not general, actually, this very particular property of L0. So they would be automatic if these were L0, these two properties. And there was also there were dynamical reasons to think that. Again, Glasner and Weiss proved that for a generic T, the natural Boolean action, let me not go into what Boolean action is, of that element is Worley. So it's very complicated. It's like kind of weakly mixing. For a generic T, this group has a natural Worley action. And again, if this were L0, Worliness is automatic for ergodic actions of L0. So you would get this result for free if this were L0, if this group were L0. So there were all these indications that we are getting L0 as a group. And so the theorem here, so the question is this actually L0? And the theorem is that it's not. So for a generic transformation T, this group is not isomorphic to L0. So it's not only that it is not the case that for a generic T, I don't get L0. In fact, for most T's, it is not L0. L0 can happen only on a small sliver on odd. It will happen by Glasner and Weiss somewhere, but it is not. L0 will show up only on a very exceptional set. So are there any questions about this motivation and about the statement of the theorem? Okay. So then,
I have a question about what is the condition that you need to ask for T to get the isomorphism?
I mean, to get an isomorphism, there is no easy condition.
There is no easy condition. Okay.
There's no easy. There's actually if you look at, so I think the following is open. You can look at all the T's such that T C is isomorphic to L0. You look at all those T's, this set is non-empty. And it's not clear what is the descriptive complexity of this set. On the face, it looks like sigma 1, 2, and it might just be sigma 1, 2, which would indicate it's a very complicated property, being isomorphic to L0.
Okay.
But not crazy. I mean, it's projective, but no. Yeah,
Thank you. Yeah,
Mhm.
thank you.
Mhm.
Also about that equivalence class, do we know if it's meager or something?
Okay, so for this equivalent, so this is an equivalence class with respect to that equivalence relation. And
Yes.
this equivalence class is meager, right? This is what this theorem says. But it does not, so actually, this is maybe the main question in this kind of area. It is still possible that there is a comeager equivalence class. This is not known whether there is one. It cannot, the only group that was a good candidate for this being comeager is now ruled out. So the only good candidate is ruled out. But it's not known whether there is another group, if I can put another group, Polish group G here, and make this set comeager. That's possible. It's unlikely if you ask me, but possible. Is that what you asked about?
More or less. And is there a good, maybe not as good as L0, but is there a good candidate for it?
No, there is no, as far as I can tell, there is no other candidate.
Okay.
So, I mean, yeah, let me, you could, I mean, daydream, you can just kind of daydream what it might be. It might, you see, so there are various restrictions. So these groups, generically, they are very similar, as I already mentioned, they are very similar to L0. So on a genic, they are very similar. So this, your candidate would have to be very similar to L0 without being L0. And then one could somehow maybe think that there could possibly be some kind of a Fraisse, if you are familiar with this Fraisse kind of generic construction involving toruses, and you take some kind of a limit that will be similar to L0, but not easy to describe. But it's unlikely. My bet is there is no G like that. Okay, so any other questions? Oh, by the way, I'm running very late here on my slides. This is half of the talk. How much time do I have?
Don't worry about that. You can take the time that you need.
Okay, so let me, thank you. So let me just, this is a rough outline of the proof. So the proof is somewhat kind of maybe unusual for proving something like this. So one proves, there are 2 points. So one proves the following 2 points. So I will have to, I will explain a little bit about these notions that are undefined on these slides. So first of all, if one proves that a conditional thing, that if this were true for a generic T, then there would be some ergodic action of L0, measure preserving action of L0. They call them Boolean actions, but let's just say ergodic measure preserving action of L0. There would be one such that will have spectral properties similar to spectral properties of a generic T. So there is many things here that I haven't defined spectral properties. I'll come back to it. So there will be some action with certain special properties if this happens, if this were L0 for a generic T. And on the other hand, one shows that there is no generic Boolean action of L0 with such spectral properties. So this is an outright theorem that there are no actions, measure preserving actions of L0 that would have certain specific spectral properties. This is an outright theorem, and then this clashes with this conditional statement under this assumption. Okay, so now the problem in the first part is maybe not mostly, but a lot of the problem in the first part is conceptual, to define what are spectral properties of L0. And in the second questions, once this is resolved, this is where the technical work, difficult technical work resides. This is where the technical difficulty is in point 2. So I have to say a little bit now about the spectral properties. So I'll just roughly outline it. And so if you look at ergodic theory, you see that these properties that made TC similar to L0, there were certain structural properties, there were dynamical properties, but spectral properties were missing. It's not that they contradicted anything, but they were kind of conspicuously missing there. So this is what one should look at probably. As it turns out, this is actually correct. So spectral behavior of a generic T. And I would like to keep it on kind of a somewhat abstract level, not to go into the definitions, just to see, just on an somewhat abstract level, see what kind of objects we get and what kind of contradictions we get later on. So this is a sequence of several papers due to Choksi, Nadkarni, Katok, Stepin, and the last result was that due to Delhunko and Lemańczyk in '92. And what's going on here is for every T, in fact, okay, for every T, let me just talk about T. To every T, one can assign a sequence of measures. And these measures are on a specific space, on the circle. So no matter how strange on the spaces on which T does its action, one can assign in a canonical way a sequence of measures on the circle, and these measures are such that the next measure is absolutely continuous with respect to the previous one. So they kind of go down. They are down. I mean, they are getting smaller and smaller. And this main one here is called the maximal spectral measure, for obvious reasons. It's the biggest one. And this is a bit of a lie, what I said here. One doesn't really associate with T a sequence of measures. One actually associates a sequence of classes of measures. So we don't get a measure here. We get a class of measures. Where by class, I mean that I identify two measures if they have the same measure zero sets. So I get the same, not measures, but measure types. So this main one, this biggest one here, will be called the maximal spectral type. So with every T, I can associate this maximal spectral type. So what Delhunko Lemańczyk do, they look at, never mind how it's done, it's just certain, and the spectral types, they in some sense classify the measure, the transformation. They know everything, not every, but up to what they call unitary equivalence, this measure is completely captured by the sequence of this, the transformation is captured by the sequence of measure types. So for every T, we can look at this maximal spectral type. And what Delhunko Lemańczyk and these previous people earlier look at, they actually look at, you can take T and you take the powers of T, still measure preserving transformation, and you look at maximal spectral types of these powers now. So you have infinitely many. For each power, you get a spectral type. And then what they proved is that one can now there's a multiplication measure called convolution that comes from the multiplication on the circle. And one can, what this theorem says, that one can also take convolutions of these measures. So never mind what it is, it's some type of multiplication of the measures. And one can take one sequence of powers, take the convolution, say, look at spectral types, take the convolutions. And another sequence of powers, L1, Ln through Ln, and then L1 prime through Ln prime, and do the same. And one get one one convolution and another convolution. And it turns out that except for the trivial situations, for a generic T, these two measures will be orthogonal. So these two convolutions will be orthogonal. The trivial cases when the powers are, one sequence of powers is just a permutation of the other sequence of powers, in which case we get the same measures. So in any case, this is just this is what we get for this strong orthogonality condition for the Hunkel-Meinzig. I'll just call it the strong orthogonality condition. And I'll now look at the spectral behavior of L0. So what is that? So this was not known. And what one wants to look at, in fact, is at unitary representations of L0. So how will we construct the unitary representations of L0? So these are homomorphisms, continuous homomorphisms from L0 to U. What can they look like? And the reason, there is a way of constructing those. So given one way to do it is the following. We look, so remember, L0 has the measure lambda behind it. These are functions measurable with respect to lambda. With lambda, I can associate a Hilbert space, namely all square summable complex valued function with respect to lambda. So that's a separable Hilbert space, infinite dimensional. I can look at unitary transformations with respect to, for that Hilbert space. And then we can ask, what kind of homomorphisms I can produce here? One easy one is this. So take an element of L2 and just multiply it by an element of L0. So I take an element of L0, I have to act on L2. I have to form from phi, I have to form a unitary transformation. So I can, here it is. I take F and I just multiply it by phi. A very simple transformation, U phi. Okay, so that's one. But very quickly you see that one can do a little bit more. Instead of looking at L2 of lambda, I can go to a measure that is absolutely continuous with respect to lambda and do the identical thing, just multiply by phi. And things will work out. This is a unitary representation now in U of L2 of mu. But one can do a little bit more. Just keep pressing it. So instead of multiplying the function by phi, I can fix an integer, fix it, and multiply f by the power, the kth power of phi. That's still if k is fixed, mu is fixed, it is still a unitary representation. And then, okay, so we have a bunch of those. What else can one do? And one can do the following thing. One can do one more thing. One can do a several dimensional version of it. So what one does is this mu is now in the product of 0, 1 with 0, 1. That's your mu. And I look at L2 of mu, so functions here. And I have to have a way, if I take phi from L0, so I have phi on both coordinates, I have to have a way of acting on this function in L2 by phi. So how one can do it? Well, I can take two powers, K1 and K2 of phi, take projections from the product to the coordinates and pull back phi to the power K1 and phi to the power K2 to the product and multiply F by the power of these two pullbacks, by these two powers, by pullbacks of these two powers. And this works. This is again a unitary representation. And this is all that can be done, in fact. So let's just recall what we've done. One can form a multi-dimensional version of what I did above. The only thing that's important here is that I go to the product of 0, 1. I have a measure on it. I have to assume some properties of this measure. Let's not worry about it. Marginals can have to be absolutely continuous to lambda. That's kind of expected because you see this mu here had to be absolutely continuous with respect to lambda. So there is a mu on this product, and there is an assignment of powers to the coordinates of 0, 1 to n. These are these two powers here that I was pointing out. So now I have several of those powers. Okay, so I will call such representations atomic representations. And there are, you see how this whole business is coded. It's coded by mu, and okay, I have this K1 and K2, these powers, maybe more powers. These powers are coded by a certain, this sequence of powers is coded, I will not go into it, by a certain countable semigroup. An element of that semigroup encodes n, so this how many coordinates I take, and it encodes how these powers are assigned to the coordinates. So I'll have an element of the semigroup. It's very simple to define, but I don't want to spend time on it. This is how it's done. It's very simple. Let's just not worry about this. But there is an algebraic structure on the codes of, so it's a countable code, it's a code from a countable set and a measure. That's all there is to it. And there is an algebraic structure of the semigroup on the codes. That's all that we need to remember. So a long time ago, I proved that a unitary representation of L0 without non-zero fixed vectors, so this is some non-triviality assumptions, let's not think about this, then disk C is built from atomic representations. Each of these atomic representations is determined by a code coming from the semigroup A and by a certain measure. So I take for every element of this fixed semigroup, countable semigroup, I have these codes. With each code, I have a measure. And then I do this atomic thing that I just did on the previous slide, and I take some kind of a product, L2 product. So this sequence determines C is uniquely determined up to mutual absolute continuity, and it determines C up to the unitary equivalence. So this is above is true up to certain multiplicity. That doesn't matter here. So in any case, every C is actually a sequence of these is actually a sequence of these atomic representations. So let me now, based on that, so now we know what spectral behavior is. Let me now say what is the geography of the proof of this proof of the main theorem. And this involves a theorem of a student of mine, Etedadi Al-Yabadi. So we study these unitary representations of L0 with non-zero fixed vectors. So the main issue, it will turn out, so this is what one should pay attention to. We have this unitary representation, Xi. This gives rise to the sequence of measures indexed by the codes coming from the semigroup. And as it turns out, one has to pay attention to and compare the following two measures. So one can take two elements of the semigroup, X and Y, and one can form X plus Y in the semigroup. Because X plus Y is in the semigroup, I will have a mu attached to that new code. On the other hand, one can externally take mu X, mu Y, and take the product. As it turns out, this is by the way things are done, these two measures happen to live on the same product of the intervals. So they live on the same space. And then it makes sense to compare the two and ask, are they absolutely continuous with respect to each other? Are they orthogonal with respect to each other for various X's and Y's? That's what is being done. So given a representation, we get these measures from my old theorem, and then we make these comparisons. Okay, so Del Junco-Lemaitre condition for L0, so this is done by my student, was done by my student Etedadi Al-Yabadi. He looked at an arbitrary, non-trivial, this is non-triviality, unitary representation of L0, and using, this is actually kind of, these proofs are kind of descriptive set theoretic in nature. This is some kind of a calculus of meagerness. He assumed that for a generic phi, so this was, I gave him as a problem, say, look, take a generic phi here in L0, forget about odd, just L0, and one can formulate, so one can take, if one is given a representation for a given phi in L0, one associates a unitary operator in U. This unitary operator, just like elements of odd, have maximal, they have these measures. It's not just for the elements of odd, it's also for the unitary operators. They have these maximal special spectral measures. One can still take the powers, take maximal spectral types of the powers, take the convolutions of those, and assume, just make the assumption that for this unitary representation, the Delhunko-Lemańczyk condition holds. Just formally assume it. What does it mean for the representation Xi in terms of the measures from my old theorem? And he made a precise translation. There is actually a precise translation from the Delhunko-Lemańczyk to a condition for the measures from my old theorem. But in particular, if the Delhunko-Lemańczyk condition tells us, implies by Etedadi Aliabadi, that for all xy in A, this product measure is orthogonal to the measure computed for the sum of x and y. We have this orthogonality for these two measures that we are paying attention to, for all x and y. So this gives you some, this is a kind of nice result, because from a generic T, like it's a probabilistic condition, topologically probabilistic condition, we get a kind of a deterministic condition on these measures from the theorem, the classifying theorem for unitary representations. Important thing is these measures here are always orthogonal. Okay. So now, for the main theorem, technically the main theorem. So notice that if I have, so now how does this unitary stuff connect with odd? Assume I have a Boolean action. So I have a homomorphism from a group to odd. So every element of G here gives me zeta of G in odd, gives me a measure preserving transformation. I can associate with it a representation on L2 of the Lebesgue measure. How do I do it? Well, I have to, given an element G in my group, I have to act on an element from L2. How will I act? I will take zeta of G, I will end up in odd, and I will pre-compose it with F. I have to put -1 here to make it a group homomorphism rather than anti-homomorphism. So every measure preserving action of the group G gives rise to a unitary representation. These are special unitary representations, not arbitrary ones. They are called Koopman representations. They come from the 30s. It's an old idea that an action, measure preserving action, gives you a unitary representation. Okay, so now what? So here is the theorem that resolves the issue. If I have this special type of a representation associated with an ergodic Boolean action of L0. So on the previous slide, the group here is L0. So I assume I have a measure preserving action of L0. I form the unitary representation out of it using this Koopman trick. What happens is then for all C's like this, I have this absolute continuity result. So if I form my product externally for xy coming from the semigroup, and I internally do the sum and compute the measure mu for the sum, this measure here is going to be absolutely continuous with respect to that measure. So I take Xi here. This is a representation. I run my old theorem for this. I get the mu's for Xi. And because Xi was Koopman, I get this absolute continuity result between them. So I get actually continuity, absolute continuity rather than orthogonality for special representations. So these are we start getting some tension that in some situations we are getting this. And this is almost the punchline. So how do we do the proof of the main theorem? So I have a proposition below that gives a connection with the Glasner-Weiss question, and it uses both Etedadi-Aliabadi's theorem and Delhunco-Lemańczyk's theorem. And the proposition is as follows. This has to do with point number 1 of the outline of the proof from the beginning. So assuming that for a generic T, this is isomorphic to L0. Assume this happens. Then I can find a single, there will be an action of L0, Boolean action, measure preserving action, such that its for its Koopman representation, I get the orthogonality condition. Orthogonality condition for this particular ergodic Boolean action of L0. For the Koopman representation, I get the orthogonality condition. This uses a descriptive set theory in a crucial way. It uses a version of this Kuratowski-Ulam theorem, this Fubini type theorem, uses Etedadi-Aliabadi's theorem that Delhunco-Lemańczyk type of condition causes orthogonality for the measures, and uses actually the Delhunco-Lemańczyk theorem that if for a generic T, I do get orthogonality. So in any case, I put all these things together and get this proposition using a kind of descriptive set theoretic argument of the Kuratowski-Ulam type. Suffices to say here that there is I get an action for which I have orthogonality, but that's trouble. This is not just tension. This is outright contradiction. So I have that from my last theorem, where the most technical work was done, for all ergodic Koopman representations of L0, I have absolute continuity. But I just, using all this work that I just mentioned, I produce some ergodic Boolean action for which I get orthogonality rather than absolute continuity. And this cannot stand. If I have for all xy, I have this and that, this causes all these measures mu x to be 0. And therefore, this action that I produced here could not have been ergodic. It's a trivial action. So I get a contradiction. So let me, so I get a contradiction, and let me finish here. And sorry to go over time so much, but okay, that's it. Thank you.
Thank you, Professor Solecki, for a very good talk. So we can go for, we have time for question. I have to go, but we see you next week, but Julian could attend the question sessions. So thank you, Professor Solecki, and Julian,
thank you. Bye.
Yeah, goodbye. I will to stop the recording.